Are you able to see my screen?
Yes, sir.
Okay, fine. So let us resume the discussion we were having in the last class, which was on principal component analysis, also known as PCA. So just to quickly recap, so suppose the motivation behind this is dimensionality reduction. That is to say, we have high dimensional data. And I want because high dimension data is difficult to process because of storage as well as computational limitations. We may want to reduce the high dimensional data to low dimensional data, so that because that will help me to or that will make my computations and storage easier. However, I do not I cannot just throw away some of the dimensions. I want to either retain the useful dimensions of the data and throw away the non-useful dimensions, or I want to create some new dimensions which will be useful and project the data along those dimensions. So if you remember, there we considered some examples where the data was like this, right? So in this case, we are like in this case, for the sake of visualization, we are considering only two-dimensional data. That is, there are basically we are considering that there are two attributes. Now if if this is the way the data is distributed in the space of the space defined by the attributes, then like we can understand in this case, or we discussed yesterday in the last class, in this case, that this x1 is not useful and this x2 is useful, and the reasons given for that was that there is very low variance along x1. That is to say, for all the data points, this x1 value is nearly the same. On the other hand, x2 is is more discriminative. That is, the different data points can have very different values of the x2 feature. So this has high variance. So in this case, if we have to this two-dimensional data, if we have to consider in only one dimension, I would simply drop the x1 dimension and represent the data only according to their x2 coordinates, right? But now if we consider this kind of a data where the variance is reasonably high along both x1 and x2, in that case we cannot do something like this. That is, we cannot either give away x1 or give away x2. So in such a situation, what we can do, we observe that although the variance is not is or I mean the variance is reasonably equal along both x1 and x2, but there exists a direction like this which we may call as w. Now exactly which direction that is, we don't know, but let us say that there exists some direction like this called w, and the variance of the data is quite high, or is maximum along that dimension compared to say x1 or x2 or anything like that. So what did we decide? We decided that we will project the data according or along this dimension. So that is to say, as some of you only pointed out, what we really need to do is we want to drop perpendiculars from the each data point onto this direction, and the points which we are getting like this, these new points which we are getting, these are basically our new data points after reducing the dimensionality. So after, like, what we are trying to do is that instead of the data being defined in this space, the space defined by x1 x2, we are now doing a change of basis. That is so change of basis is something which we are all familiar with. So so in the two-dimensional space, these two define a basis. Like this is the standard basis. These are basically called the 1 0 vector and the 0 1 vector, or rather the in other words, this is sometimes called the unit vector the standard unit vector e1, and this is called the standard unit vector e2, right? Now but however, we can always replace these unit vectors by other other pairs of unit vectors. For example, this and this. right? So the I may call this as f1 and I may call this as f2. Similarly, like other possibilities are also there. For example, this one and this one. This I may call as G1 and this as G2. The important thing to note in these cases is that in all the cases, the unit vectors which I am defining, they must satisfy two properties. That is to say, they must be that the vectors must be orthonormal, which means that both of them should be unitary and they should be perpendicular to each other. So like E1 is, as you can see, 1 0 this vector, and E2 is this vector 0 1. So as you can understand, E1 is unitary, its norm like its L2 norm is 1. Similarly, E2 is also unitary, and as it should be obvious that E1 dot E2, or rather E1 transpose E2, is equal to 0. The same property will also hold for F1, F2, etc. That is to say, L2 norm of F1 is equal to L2 norm of F2 equal to 1, and also F1 transpose F2 is equal to 0. Same thing for G also. Now what we are saying in this case is that x1 x2 in this case define the dimensions of the data. I am suggesting that instead of going for this pair of bases, I will consider this W as a basis vector. Of course, it cannot be one basis vector, so it will have to have another one. So that will be some vector which is perpendicular to W. So let me denote it by this in this way. W perp. Okay, so like in the language of linear algebra, this notation, what I have written here, W perp, this basically means a vector that is perpendicular to W. So W and W perp, these two define an alternate basis for the data space. So now W part we are not going to think of as of now. So it's like W is the dimension or vector along which the variance of the projected data is maximum. That is what we wanted, right? So first of all, what is the how do I define what is the projection of the data along any direction W? The answer is so x1. So remember that W is basically in this case a two-dimensional vector. So if the data lies in general, if the data all the data they lie in the d-dimensional real space, then the direction W along which they are going to be projected, that is also will have be a like it will lie in the d-dimensional real space. Okay, so now the projection of the vector along W is defined in the following way. This is x1 transpose W times W. This is x2 transpose W times W. So this is like the projection of the data x1 on or along W. This is the projection of data x2 along W. Similarly, xn. So if you look at these quantities, so here you can see that there is the thing which is the quantity that is put inside the brackets. This is basically a scalar quantity, right? It's like, so as I have already said, W is a d-dimensional vector, x1 x2 etc. These are also d-dimensional vector. So what I am doing here is basically a dot product between two d-dimensional vectors, which obviously has to be a scalar. So this part is a scalar, and this part W, this is like you can consider it as a unitary vector. Why unitary? Because like we have defined, like we have assumed that W and W perp together define an alternative basis for the whole data space, and like we have also already discussed that the basis vectors for the data set, I mean for that space, should be orthonormal which means that they are unitary and they are perpendicular to each other. So this is like an unitary vector. Okay. So now x1 transpose, so like if so like this part which is the scalar, this is sometimes called as the magnitude of the projection. The projection, as I have defined, is this whole thing which is obviously a vector. It's a scalar multiplied by the vector, which obviously is going to be a vector. But if you consider only the scalar component, that is the magnitude of the projection. So in case of PCA, like in the case of the dimensional reduction which we are talking about, what we mention or what we really want to do is to choose W in such a way that the variance of these projections is maximized. That is the like earlier I was talking about finding that direction along which the variance of the data is maximum. So in this case there are only two directions, x1 and x2. Along x1 the variance was low, along x2 the variance was high. So in this case like I have decided to do away with x1 and x2 and instead project the data on this new space defined by W and W path. So, and specifically W is that I want W to be that direction along which the variance of that data is maximum. So, so what I need to calculate here is the variance of the projections of the data along W. That is, if you consider this point or this point or this point, etc. Like you now you can just focus only on this single line. There is a like of course this W is it's a two-dimensional vector, but for some time now you can forget everything. You can just focus on this one dimension W. So basically it's like you have a line along which you have got these points. These points which indicate the magnitudes of the projections. So there you have got n values like this. You just need to calculate the variance of these values. Okay, and so what we did in the last class is that we wrote a formula for variance which which was written in some in a particular way using the usual definition of variance, and then we wanted to choose W such that that variance is maximized, right? So it was somewhat like this, right? Because we had assumed that like of course we know that the so not xi, sorry, it's like I equal to 1 through n whole by 1 by n, and we had also like we may assume that the data is centered, that is to say this quantity is equal to 0. So if this is not the case, that is like the data is something which is in your hand. So like if this is not the case, then you can always do this. That is to say you can replace the data x1, x2, etc. by x1 tilde, which is like x1 minus x bar. Similarly, x2 tilde is equal to x2 minus x bar. Where what is x bar? X bar is this like the mean of all the data that is given to you. So once you do this, then you have basically replaced the that is now you will no longer work with the x1, x2, etc. Vectors, but instead you will deal with x1 tilde, x2 tilde, etc. So it's basically nothing but a simple translation or a shift of origin. Instead of keeping the origin of the data at 0, 0, you are shifting the origin to this x bar, where x bar is defined in this particular way. So instead of taking the when I'm taking the projections also, instead of taking the projections of the original data, I take the projection of this the tilde data, that is the shifted data. And the shifted data has this property, which should be obvious by the way the origin has been shifted, that the mean of will be equal to 0. So basically this is what the that variance, how the variance was defined. So this we wrote in a slightly different way, and then we like what we finally arrived at is that this maximum variance V is going to be an eigenvalue lambda, or the first eigenvalue lambda, largest eigenvalue lambda, and this W is going to be the first eigenvector, the corresponding eigenvector U1 of what? Now of a matrix called C, which is defined as xi tilde transpose summation over I. Okay. So as you can understand, here we were taking the inner product between x and or xi and w. Now here what I am doing is basically I am taking the outer product of each data vector with itself and then adding it up over all the data vectors. So the data vectors xi, so as I already said, xi is what? Xi lies in, it's a d-dimensional vector, or rather xi is a d cross 1 matrix. So xi tilde is of course transpose is also 1 cross d, and so if I take their outer product, what I get is d cross d, right? So it's basically it's a matrix which I call as C, and this C is also sometimes called as the sample covariance matrix. So what happens is that, so the W which we are looking for, the direction W along which the variance of the data is maximized, that W is nothing but the first eigenvector of the sample covariance matrix C of the data, of the shifted data. And what is the quantity of that variance? The quantity of that variance is nothing but lambda 1, which is the corresponding eigenvalue. Okay? And so this W, which is actually equal to U1, this is called the first principal component of the of the data. Right? So this U1 is called the first principal component of the data, and it can also be shown that this is this first principal component of the data is actually the first singular vector, or the largest the first left singular vector of the data matrix, which is X. So what is that? So let us define X as a matrix like this, where every column of the matrix is one of the data vectors. The first column is the first data vector x1, the second is the second data vector x2, etc. And there are n data points like this. So I will get n columns, each of which is d-dimensional. So this X is a d cross n matrix. Okay. So in general, of course, d is not equal to n. This is not a square matrix. Now what we are talking about is, since X is basic, like X is any matrix, it can be represented as using the singular value decomposition. So we can write X in this form: U capital sigma V transpose, which is the SVD, because SVD exists for all matrices, whether it's a square matrix or not, whether it's a singular matrix or not, whatever, we can always get a SVD of it. Now, okay, so instead of X, let's consider just X tilde like this. Let's say that we have already centered the data as they say. Now, now what is the claim? The claim is that C, we are talking about C. What is C? C is this, the sample covariance matrix C is this matrix. Xi tilde transpose, both tilde I equal to 1 through n. Okay, this is the C matrix. Now my claim, and as I have said earlier also, this is a D cross D matrix. Now my claim is that this matrix is nothing but 1 by n x tilde x tilde transpose, where x is defined in this way. Okay, so this is a D cross n matrix, D cross n, and this also is an n cross D matrix. So their product will obviously have to be D cross D. So I leave it as an exercise for you to verify that the way I have that this summation of xi tilde transpose summation over I is nothing but the product of this matrix with its own transpose. That is the outer product of this matrix with its own transpose, where this matrix is simply contains all of these data vectors arranged as columns. Okay. So this I leave it for you as an exercise to verify. Now x tilde I have already said its singular value decomposition is like this. So if you consider x tilde transpose, what we are getting is u sigma v transpose into its transpose, which is v sigma transpose u transpose. Now v transpose v is equal to the identity matrix I, so I get u sigma sigma transpose sigma times u transpose. Now like of course the n is all the like the factor of 1 by n is also there, so you can just bring it in here. So now you can understand that when we are talking about like if in the previous case where we are like where we were talking about taking the eigenvector of this C or the first singular I mean the largest eigenvalue of C and the corresponding eigenvector, these being the things which quantities of our interest, that is we were saying that the W is the first eigenvector of C, right? But C is what? C is now equal to this quantity, right? Now you can understand now that this 1 by n sigma sigma transpose, this is basically a diagonal matrix. The way sigma is defined, you can clearly work out that this is like just like these are all. This is a D cross D unitary matrix. This is also a D cross D unitary matrix. Sorry, orthogonal matrix. This is orthonormal matrix, and this is a D cross D diagonal matrix. That means what? That means that this is actually the eigen decomposition of C. That is the singular vectors of u of x tilde are actually the eigenvectors of C, and correspondingly the different singular values of x tilde like after doing this transformation are actually nothing but something like the square of the square divided by this n of the eigenvalues of C. So basically W, which is the first eigenvector or the largest eigenvector of C, is also equal to the first left singular vector of X, and it is also called the first principal component of X. Okay. Now, since I am talking about the first principal component, it also suggests that there has to be a second principal component. Now what is that? So now what we have done basically is that the data was like this, xi or xi tilde. What I did is I replaced it by the projection, that is the projected data. What's the projection? The projection is w tilde transpose xi times w, sorry, not w tilde, w x w. Okay, this is the projected data. So this is original, this is projected. Correct. So note that this is a d-dimensional vector and this also is a d-dimensional vector. Why so? Because as I said earlier also I have said that this is scalar, this is a d-dimensional vector, so their product has to be a d-dimensional vector. So now, now I define what is known as the residual xi tilde res. What is residual? The residual is that is only part of the data I have replaced in this way. So I define it as W transpose xi tilde W. Okay. So why is this like what is the idea behind this residual? The idea is that this is a two-dimensional vector and I am trying to pass it off as a one-dimensional vector by projecting it onto this W. But that means what? That means a part of it is remaining also. I cannot just throw what is a two-dimensional vector? I cannot just make it as a one-dimensional vector. The other thing also has to be there somewhere. So the question is, where is that other thing? That other thing is the residual. So if you remember, we had like our original space was spanned by these two, x1 and x2. I mean, sorry, not x1, x2, the e1 and e2, right? e1 and e2. Now from there I did a change of basis and my new space which I have now defined is defined like it. So since this is two-dimensional, it has two bases. So after change of basis also it needs two basis vectors. So one is W, which we are already talking about here, and the other, as we said earlier, is W path. Okay. So just like any vector xi tilde, earlier it was expressed as what? It was earlier expressed as the in this way, xi tilde sorry, e1 transpose xi tilde times e1 plus e2 times xi tilde times e2. Right, that way. So like, why am I saying this? So let us say that that xi tilde, let's say the data vector was something like say 4.5 3.7. Okay, let's say this was the data vector. That is the first attribute, its value was 4.5. The second attribute, its value was 3.7. Now I can write. So what I have written here, e1 is nothing but 1 0 and e2 is equal to 0 1, right? So again I leave it as an exercise for you to verify that the data like this data vector xi tilde can be written in this way. So what is the first component doing? The first thing doing, I am basically considering the projection of the data along e1. So in this case, tell me how much is the projection? So given that this is my data, tell me what is the projection of the data along E1? What's the magnitude of the projection along E1? Yes?
4.5.
It is nothing but 4.5. I mean, you can of course do the calculation here and take the actually numerically calculate the dot product and and say, but actually it's not needed. E1 transpose, the way it is defined, it simply means the first component of the data, which has to be 4.5. So 4.5 into E1, and similarly, what is this equal to? Yes, what is this?
3.7.
This has to be 3.7. So the xi tilde in that case is 4.5 E1 plus 3.7 E2. What is E1? E1 is 1 0 vector, and what is E2? E2 is 0 1 vector. So as you can understand that xi tilde, according to this expression, xi tilde will have to be 4.5 3.7, which is what it is, right? So that means what? The thing is, so any vector, so whenever I have any basis vector defined by, like any space defined
Sir,
by, yes,
sir, how you have defined the residual?
I'm coming to the residual. Just give me a minute. I'm coming back to it. So let us say that E1 and E2 are any two basis vectors. That means any like any vector, say x tilde, xi tilde, can always be written in this way: xi tilde transpose E1 or E1 transpose xi, the same thing, into E1 plus xi tilde transpose E2 times E2. Now what I have done, I have made a change of basis from E1 E2 to W path, right? So what is, so in this case, so my data can as well be written in the same way: xi tilde transpose W into W plus xi tilde transpose W perp times W perp. Okay. So this is true for any W. Now consider the specific W which we are talking about, where W is the first singular vector of X, of the data vector X. Sorry, data matrix X. So if you instead of calling it W, let me call it as U1. Okay. So now, so my data, the projection of the data along that W which we have chosen is going to be nothing but xi like xi tilde transpose U1 into U1. This is my projected data. But if this is my projected data, but my original data is xi tilde, right? And xi tilde is not the same as the projected data. So what is remaining is this quantity. And this is what I call as my residual. But what is the residual then? As I have, so I have this expression which says the xi tilde, the original vector, can be decomposed in this way. Right? This is a standard decomposition for any W. So that means if W is equal to U1 transpose, sorry, not U1 transpose, U1, then xi tilde has got to be xi tilde transpose U1 into U1 plus xi tilde transpose U time, sorry, U1 perp times U1 perp. Okay. So the residual is basically xi like this minus this, which is also equal to this. This is called the residual. So now what? So now I suppose I. So like this is the part of the data which I have basically conveniently thrown away or ignored as of now. Now, now consider that I don't want to throw it away. I want to consider that also. So so specifically, let us now consider, instead of two-dimensional data, let us consider a d-dimensional data where d is high. D-dimensional data where d is much greater than 2. Okay. So what I have, so the principal component and analysis which we did so far, that still holds, where U1, what is U1? U1 is direction of maximum variance and it is also equal to first first singular vector of X, of data matrix X, also called first principal component. So so basically now right now I have so my data is d-dimensional, where d is much greater than 2, but so far I have got only one dimension, which is and what is that? That is the direction u1 along which I have projected the data. So what was originally a d-dimensional vector has now become a one-dimensional vector along this direction you want, but which of course means that some residual like this is remaining. Now I may not want to leave that much of residual. I may think that why should I the data may be quite high, d-dimensional data, like let's say d is equal to 35. So I may say that I do not the original data is 35 dimensional. I do not want 35 dimensional, but I can do maybe 3 or 4 dimensional I can handle. So only one dimensional data I may not, I mean I can afford more dimensions than one. So then what will I do? I will look for the second principal, I mean the second principal component, what is W. So again, so now what is going to be W? W is going to be basically the direction of max variance of the residual. Right. So as I have already said, that first there was the data which I called as xi tilde. From that data, I am removing a part which is going in the direction of w, or in this case u1. So but after removal also I am left with this amount of data, the residual. So the residual data, I now am interested in projecting the or basically projecting the residual data along that direction for which there its variance is going to be the maximum. So that means what? Pretty much that's pretty much the same thing as we had done earlier also. What we are like what we want to do is I want to maximize W transpose, let's say I will call it as C1 now, C1 of W. Okay, sorry, wait, sorry. Let me so the residual data which I have defined in this way, let me define it or let me just denote the residual data by let us say yi tilde. Okay, just for the sake of just for the sake of ease of notation, yi tilde is this quantity. So what do I want to do? I want to project the data W, along a direction W, such that its variance is going to be maximized again. So in other words, so what is the projection? The projection of the y's along the W is going to be W transpose yi tilde, right? And so I am trying to, so now you can convince yourself that whenever I say, like, so xi regarding xi tilde, we had this relation, right? We had summation of xi tilde is equal to 0. Okay. Now what am I saying? I am talking about y. I am now, instead of xi tilde, I am talking about the variance of yi tilde. Now what can I say about the summation of yi tilde? The summation of yi tilde, the way it has been defined, is summation of xi tilde minus, I am going to put a summation over this quantity, minus xi tilde transpose u1 into u1, right? So now, as you can understand, this summation is over I. So u1 and u, like this u1 is independent of I. So what is going to happen is that this summation is going to be drawn in. So I am going to write what I have already written as I bring the summation inside xi tilde whole transpose u1 times u1, right? But what is summation of xi? Summation of the xi is, this is 0. So this, so it's going to be the 0 vector transpose u, which is of course 0, and then the 0 scalar into u, which is also 0. So this part also becomes 0, just like this part was 0. So we can understand that because xi tilde is summation of xi tilde is equal to 0, summation of yi tilde is also going to be 0. So that significantly simplifies the calculations here for us. So I am just interested in, when I am saying variance, as you know, variance is equal to mean of squares minus square of mean. But the mean is equal to 0. So I am focusing only on the mean of squares like this. And what is this equal to? This is equal to, again, y by 1 by n into yi. Sorry, let me write it as W transpose yi tilde transpose times W, right? Almost exactly same as what we had got last time. The only difference is that yi like yi is now like defined in this way as the residual. So so now what are so once again we do the same as what we had already done last time. We have what constant do we have on W? The constant is that it has to be unitary, that is W transpose W is have to be equal to 1. But we also have an additional constant. What is that additional constant? Now since we have already projected the data along u1 once, so whatever is the residual, that must necessarily be perpendicular to u1, right? So whatever W we are choosing, it has to lie in this thing u1 perp. So which means that now W lies in u1 perp means what? It basically means W is perpendicular to u1. So this is an additional constant which we have got in this case, right? So note that so why is this the case? That's so, like, why does it have to be perpendicular to u1? Because we have already projected the data along u1, and the residual which we are considering, that residual is actually this is the expression for the residual. It lies in or like the basis for that for the residual is U1 parp. That is, and what is U1 parp? U1 parp is basically a subspace which is orthogonal to U1. So whatever W is, whatever vector W is, it has to be perpendicular to U1. So this is an additional constant. Now, if you so what in such a situation, what do we have to do? We just replicate the steps which we had taken last time. That is to say, we bring in the these what they call it as our Lagrangian multipliers. So
Sir,
yes,
sir, shouldn't we have taken W to be U1?
yeah, sorry, that is what we are talking is W transpose U1 is equal to 0. This is what our constant should be. Is that what you are asking? Let me write the thing again. So what we are trying to do is argmax 1 by n, the variance which is given by I equal to 1 through n W transpose yi tilde whole square, which I can also write as taking the W transpose out, I can write it as 1 by n I equal to 1 through n yi tilde transpose the whole with again W on the right hand side also. I can write it in this way because what? Because W transpose yi tilde is equal to yi tilde transpose W. Right? These two are the same thing. So accordingly, I can write, just take the W's out and I can write it in this way. Now this thing, this quantity, as I can understand once again, is basically the sample covariance matrix C of Y's. So I am trying to do this problem. Instead of C, let me call it as C2. Okay, argmax W transpose C2 W. Now the constants. Constant number 1 is that W should be unitary, that is W transpose W should be equal to 1. Also, W transpose times U1 should be equal to 0. Why? Because I have already projected the data along U1. So this W, whatever it is, it must lie in U1 path. Okay. So it's a what is U1 path? U1 path is a subspace orthogonal to U1. So any vector which is part of U1 path has got to be perpendicular to U1. So this is what the constant which we write. Okay. Now what I do, I once again I bringing the Lagrangian multipliers and yes.
Sir, why we don't take the norm U1 equals to 1?
Norm U1 equal to 1. U1 is already fixed. U1 I already know. U1 is already known. That is, considering that as a constant is not a purpose. The U1 is a constant now. The variable is W. Okay, that is the I am trying to find the problem which I am trying to solve now is regarding W. This C2 is defined in this way, which is a constant. U1 is also a constant. I do not define constraints according to constants. I define constraints according to variables.
But sir, previously all the perpendicular axes are we take the norm value equals to 1. So if constant U1, then also take the norm value is 1.
I mean it is a fact that it's like its norm value is equal to 1. Nobody is disputing that. Of course it is true, but but u1 is fixed in this case. In this case, there is no point in adding a constraint like this. The constraint is to be defined only in terms of the variables. It is a fact that u1 is the norm of u1 is 1, but writing it here does not serve any purpose for this problem. So like this is like basically it becomes pretty much like when I write the new objective function j in the same way as I had written last time in terms of the Lagrangian multipliers as plus lambda 1 minus w transpose w minus w2 as w transpose u1. So now like I have several constraints like this and now I'm not going into the details of all these things, but again what I will do is I will like take this kind of a relationship, that is I will try to choose w such that is I will basically take the derivative of the augmented objective function with respect to w, and I will equate it to 0, and finally what it will turn out is that again this w is the first eigenvector of C2. Yeah, this is what you will get. W is the first eigenvector of C2. But what is C2? C2 is this thing. C2 is equal to 1 by n I equal to 1 through n yi tilde transpose. But what is yi? Yi is defined as xi minus minus xi transpose u, like if you call it u1 into u1. This is how y was defined. Yi was defined, where u1 is the like the first eigen or the first singular vector of x. Now what happens to this C2 matrix? This you can do a bit of mathematical jugglery by bringing this one in. I write xi minus xi transpose u1 into u1 times xi, the whole thing once again taken transpose. Okay, so like here you can carry out some amount of mathematical manipulations, like so again this part I am leaving it for as an exercise for you to simplify. It's not really all that difficult, but finally what you will understand is that C2 is basically nothing but that is this covariance matrix C2, you will understand that is basically nothing but the what is remaining of the original. So this is what the original covariance matrix was, right? This is what we originally had, minus a particular quantity which you will understand after doing this simplification. And then you will understand that the first eigenvector of C2, the way it is defined, is nothing but the second singular vector of x. So what was the first singular vector of x? That was u1. Now what is going to be like once I take the residual and try to calculate the maximum variance of the residual, you will find that the w along which the residual has to be projected, that is nothing but u2, which is the second singular vector of x. So this, why it should be the second singular vector of x, that I will leave it for you as an exercise that you will understand once you actually simplify this thing. But you can convince yourself that u2 satisfies all the constant, that is this constant, that it has to be unitary. Yes, the second singular vector of x is unitary, that we already know, and it has to be perpendicular to u1, that also we know, because we know that the different singular vectors are orthogonal to each other, right? So basically
Sir,
yes.
sir, how did you formulate the J? I mean, was it taught in the last classes or
J,
something?
yes. So J, like we basically we discussed this in the last class, where we have, this is a constraint optimization problem. So note here, this is what we call as the objective function. Okay, objective. And these are what we call as the constraints. So when we have, so basically this is what we call as the constraint optimization problem. And whenever I have a
Yeah.
constraint
Okay, got it.
optimization problem, I can write it in this way, where lambda1 and lambda2 are called the Lagrange multipliers. Okay, so now basically what we have done here is as follows. We first so what is the first principal component of the data? Okay, so let's say that I have data x, which is d-dimensional data. Now I want to reduce this data from the dimensionality of this data from d down to some number k, where k is much less than d. Like say k is much less than d. So what do we first do? We first project the data along its first principal component, which is given by u1. So what happens? So then what happens to the data? Basically, the data becomes x1 transpose u1 times u1, then x2 transpose u1 times u1, etc, etc. So the so these magnitudes of the projections basically denoted in this way, xi transpose u1. These are the basically the projections along first PC, which is u1. Okay, these are sometimes also known as the loadings. Next what happens? The next is the second principal component, u2. What is u2? u2 again, like in the same way, x1 u2 into u2, x2 transpose u2, etc.
Hello, sir. You are mute, sir.
So similarly, so just like the I have shown up, we have already seen first and second principal components. Similarly, if I want, I can go for third principal component also, fourth, fifth, sixth, all the way up to kth principal components also. And these are, all of them are defined in the same way as the successive these singular vectors of x, right? So you, like in case of u3, the the projections are going to be like, again, x1 transpose u3, u3, x2 transpose u3, u3, etc., etc., where again xi transpose u3 is the loading along u3. Right? So now what are u1, u2, u3? So u1, u2, u3, etc. are nothing but the the left singular vectors of the original data matrix X. So X can be represented as U sigma V transpose, where U is equal to U1, U2, etc. Then UK all the way up to UD. So basically, in case of principal component analysis, what is the thing which we actually have to do? You just carry out, whenever you are given the data matrix of X, you carry out you calculate its principal components in this way, and then you keep on projecting the data along the first principal component, then along the second principal component, third principal component, etc. Sorry, the first I mean the first singular vector which is its principal component, then the second singular vector which is its second principal component, etc., etc. And this you do till k. Now what is k? K is like any dimensionality which you want. And so what is achieved by doing these kinds of projection? So whenever you are projecting the data along the first principal component u1, you get a variance which is equal to like sigma 1 square by into 1 by n, where sigma 1 square is its singular value, right? So this is something which we also had seen last time. Then when I am projecting the data along the second principal component, then its variance along that direction is sigma 2 square by n. Similarly here again the variance is sigma 3 square by n, etc., and so on and so forth. So basically, basically what this framework gives is that it helps you to project the entire data onto a subspace of the original space, and that subspace is defined by these k basis vectors, which are nothing but the singular vectors of X, and each of the singular vector contains a part of the data, or which is sometimes known as explains part of the variance in the data, and that variance is defined in this way. So basically that's the story of principal component analysis. So this is how we do principal component analysis, or PCA. Okay, so with that we come to the end of this class.
Sir, are you following the Gilbert-Strang book or the other? I think you showed a PDF from Stanford University.
Yes. For principal component analysis, I like what I followed is basically the PDF which we showed in the other day. So I'm going to upload that here in this Teams folder so that you can take a look.
Okay, thank you.